So in this part, let us now look at some examples of how we apply the residue theorem to different types of integrals that we have covered already. At first, let us consider the famous example, which is listed as in example 68. Find the integral of sine, let's say sine omega x over x dx from minus infinity to plus infinity for omega being positive. Now this integral, if you take sine omega x over x, we can show this is actually it's analytic everywhere. Easy to see this because if you take sine is actually x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus blah blah blah, and you can divide out of the x and there'll be no negative exponents. So it'll be, you can write the Taylor series completely with positive exponents. Therefore we say it's analytic everywhere. So we can write as follows: integral of sine omega x over x dx. Notice the denominator has got an x, which means it has a real pole. It's not a complex pole or your imaginary pole, it's a real pole at x equal to 0. So then we need to apply the methods we've just learned. So we can write this as the principal value of sine omega x over x dx, and take the imaginary part of e to the I omega x over x dx. We take the imaginary part of that principal value, and let's just now calculate this and see where it takes us. So this, so if we consider this z equals to naught and surround this entire thing by a semicircular contour as normal, so that's where you have a real pole. So now we have to hit this with the residue theorem as such. So this will be the imaginary part of pi I. Remember, this is now a real pole, so it's pi I residue of e to the I omega z over z at the point z equals to naught. Let's calculate this. That will be the imaginary part of pi I. The residue of that will be, you differentiate the denominator, you get e to the I omega z over 1, and z is naught. If you plug in z equals to naught, you end up getting the imaginary part of pi I. And the imaginary part of pi I is just pi. This means that the integral from minus infinity to plus infinity of sine omega x over x dx is pi whenever omega is positive. If you take omega to be negative, or let's take it to be 0, integral of sine 0 over x will be 0 over x, which is 0. So it'll be 0 whenever omega is equal to 0. And if you have sine of a negative omega x, it's minus sine omega x, it'll be minus pi. It'll be the result if omega is less than 0. These are the three options that one can get to. The very interesting thing about this problem here is that this is an interesting note. It's a side show, but it's interesting to note that sine omega x over x is actually a continuous function. You may recall this from your first year of calculus. The limit of sine x over x, x approaches 0, is actually 1. So the function looks like that. And if you go on to the other side, it's totally continuous to infinity. At 0, it has a value 1. But the integral is discontinuous. The integral is discontinuous. And in fact, the integral is either pi minus pi or 0. So it has three possible values, and you can see this is a discontinuous function. So that's a very interesting fact about this particular problem at hand. All right, now let's consider some other examples and see how we can apply the residue theorem in each case. Let's take example 69. We won't look at the details, but you can work through it once you get the crux of the matter. Example 69. This problem here requires us to calculate minus infinity to plus infinity sine x dx over x into x squared plus 4, x into x squared plus 4. So you can see clearly that this has poles at z equals to 0 or z squared equals to -4, whence you can get z equals to plus minus 2i. If you had to plot that, the poles would be 2i is there, 0 is there, and minus 2i is there. Surround this by a contour of this type, a semicircle contour, and there are only 2 points that are in the game. So you can write now, using principal value, integral minus infinity to plus infinity sine x over x into x squared plus 4 dx is actually the principal value. You take the imaginary part of e to the I z over z into z squared plus 4 dz. And we can now interchange imaginary because we are using the principal value. So it can become the imaginary part of e to the I z over, let's multiply this out, z cubed plus 4z z. Okay, so to find that answer, we have to take the imaginary part of. Now there are 2 poles that are relevant. So one is that 2i, that's a standard complex pole, so it's 2 pi I residue of e to the I z over z cubed plus 4z at the point z equals to 2i, plus the other one is half in and half out, so it's a principal value, so it's pi I residue of e to the I z over z cubed plus 4z, this one at z equals to 0. Now it remains to compute this. This one will become the imaginary part of 2 pi I. Work out the residue of this, leave it as e to the I z. The bottom you differentiate, you get 3z squared plus 4, and then you plug in z equals to 2i. Here you do the same thing. Differentiate the denominator, e to the I z over 3z squared plus 4, and plug in z equals to 0. Continue simplifying this. 2 steps, you should end up getting pi over 4 into 1 minus 1 of e squared. That should be a straightforward calculation to complete on your own. Now, let's have a look at some of the tutorial problems. So let's discuss some of the tutorial problems and see what are the main strategies to go forward with each one of them. Now we'll see the 3 different types of problems we are emphasizing in this course here. If you take your notes and look at 53a, where you go to calculate minus infinity to plus infinity dx over x to the 4th plus 1 dx, we've got dx already. You'll notice here there are only the poles here are all complex. They're complex or imaginary poles. To find the poles, we need to solve z to the 4th equals to minus 1. In other words, r e to the I 4 theta equals to, minus 1 is here, the angle there is pi. So it's e to the I pi plus 2k pi. So that straight away gives you that 4 theta is pi plus 2k pi, and then theta is pi over 4 plus k pi over 2. So we'll get now coordinates for z. Z0 equals to e to the I pi over 4. The radius there, of course, is 1 in this case here. Z2 is e to the I and k is 2 is half plus 1/4 is 3/4. Z3 and Z4 you should realize are not relevant because when you plot these here, so Z0 makes an angle of 1/4 pi, it's there. Z1 is 3/4 pi, it will be there. Z2 and Z3 will be on the other side. These are irrelevant. When we throw a contour around these, we are only going to be covering the top half. Those are the only two ones that are relevant. So then you could say that the integral is 2 pi I residue of 1 over z to the 4 plus 1 at z equals to e to the I pi over 4 plus the residue of 1 over z to the 4 plus 1 at z equals to e to the I 3/4 pi. And to work out the residue is very straightforward. 2 pi I, you're going to take 1 and differentiate the denominator. So it's 4z cubed. And you plug in e to the I pi over 4. Plus, likewise, yeah, 1 over 4z cubed. And you plug in z equals e to the I 3/4 pi. Crank this out, and at the end of the game, you should get pi over root 2 as the answer. We'll leave that to you to sort out yourself. Now, moving on. Let's take another example. 54a. For a, the type here is integral minus infinity to plus infinity, x cos x dx over x squared minus 2x plus 10. Now, the presence of cos here suggests that it's a Fourier type integral. So you'll have to use the fact that you can break up e to the ix into cos x plus I sine x. So the poles, let's see what type of poles. There's certainly no real poles, so we don't have to use principal value here. The poles will be z squared minus 2z plus 10 equals 0. And you can check that that's 1 plus minus 3i. Plot this. 1, 3 is there. 1 minus 3 is there. So it's only the top pole that really matters. So then you can say that this is 2 pi I. Well, actually what we should do is write this as the real part of, because it's cosine, we'll have to take the real part of the integral from minus infinity to plus infinity, x e to the I kx dx over x squared minus 2x plus 10, the real part. So it's the real part of. Now we can hit this with the residue theorem, and we can get 2 pi I residue of z e to the I kz over z squared minus 2z plus 10, and we will be then plugging in z equals to 1 plus di. There's only one pole of relevance in this problem. So we need the real part of 2 pi I. Now the residue here will be z e to the I kz. Differentiate the bottom, 2z minus 2, and plug in z equals to 1 plus 3i. I'd carry out the entire operation. At the end of the game, you may get pi over 3 into 1 plus 3i e to the minus 3 plus I. Check if you can get that result on your own. That solves problem 54a. Well, actually, we need the real part of that. So at the end of the game, the real part is just pi over 3 e to the minus 3. We need the real part of this. So the e to the minus 3 cos 1 minus 3 sine 1. You see, you'll have to break up e to the minus 3 into e to the minus 3 times e to the I. E to the I is cos 1 plus I sine 1. That's radians, of course. Now consider problem 54C. 54C. This problem is the minus infinity to plus infinity cos x dx. So it's looking like a Fourier category. X squared plus 1 into x squared plus 4. So it's a Fourier type. You have to take the real part of, there's only for principal value here, minus infinity to plus infinity, e to the ix over, well, x squared plus 1 into x squared plus 4 dx. So we have to find that integral there. The poles in this case here will be z equals to plus minus I, z equals to plus minus 2i. If you had to plot these, you get 2i, 1i, minus I, minus 2i. Surround that by a contour like that. So your integral works out to be 2 pi I residue of e to the iz over, let's multiply the bottom bound, z squared, z to the fourth plus 5z squared plus 4 at z equals to 2i plus residue of same thing, e to the iz over z to the fourth plus 5z squared plus 4 at z equals to I. Right, so there's no principal value, therefore it's 2 pi I. So to compute this, that's 2 pi I. The residue will be e to the iz over, differentiate the denominator, 4z cubed plus 10z. Then you plug in z equal to 2i plus, same thing, e to the iz over 4z cubed plus 10z, putting z equals to I. And at the end of the game, oh, well, I don't know what the final answer is here, but in any case, you've got to crank this out and get the final result there. You can find the answer in your textbook. Right now, one more in the same vein. 54F has got a slightly different approach, almost the same kind of idea, but here is a repeated root in the denominator, so we might have to handle this slightly differently. 54F. Let's look at the crux of the matter. Minus infinity to plus infinity. X squared cos x dx over x squared plus 1 all squared. Okay? So notice that the numerator has got a lower power than the denominator actually, so it's going to be convergent. It's most likely convergent. So we need the real part of minus infinity to plus infinity, x squared e to the I kx over x squared plus 1 squared dx. Now, if you find the poles, there are only two, z squared plus 1 naught to z equals to plus minus I. The only one of relevance is I. You surround that by that contour, only I is of importance. So the integral is actually 2 pi I, the residue of z squared e to the I kz, all upon, so there are many ways to do this. You can say this is z plus I squared into z minus I squared, and you want the residue of z equals to I. So you can say it's 2 pi I, residue of, let's perform a bit of a disguise here, z squared over z plus I squared e to the I kz over z minus I squared at z equals to I. How does one find a residue of that type? Well, at the bottom you've got a pole that's repeated with I. It's 2 pi I. We have to now invoke the differentiation rule. We have to take ddz of the numerator because squared at the bottom, we only do the differential, the derivative once. So we differentiate z squared over z plus I squared e to the I k z, and then plug in z equals to I at the end of the game. Carry this out a few times, right? You have to use differentiation here using the rules of quotients. And then at the end of the day, you will be surprised to see that actually all things cancel off and the result is 0. Fine. Let's now look at another type of problem. This time we're looking at problem number 55. So now the style is slightly different. 55a, integral minus infinity to plus infinity, sine x over x into x squared plus 1. Notice now you have sine x, so it looks like a Fourier type, but you also have this guy here, x, which is a real pole. So you now have to use the principal value. This will be the integral of the imaginary part of e to the ix over x into x squared plus 1 dx. And so now you have to be able to use the to switch the imaginary. You can now that with the principal value idea, e to the ix over x into x squared plus 1 dx. Now it's perfectly legal. Then you find here that the poles are z equals to naught, z equals to plus minus I, usual naught, I minus I, surround the contour of that type, and then you can write down integral to be 2 pi I, residue of e to the I z over, well, let's multiply the denominator out to get z cubed plus z at z equals to I, plus pi I, this is the principal value, e to the I z over z cubed plus z at z equals to naught. Okay, by now you should be an expert at this. So you carry this out and you will get pi I 1 minus e to minus 1. And we want the imaginary part, and that will just be pi 1 minus 1 over e. Imaginary part of that. 55d. This problem is got minus infinity to plus infinity. Sine x minus x over x cubed dx. You find there's a real pole at x equal to 0 here, of course, but it's also got an x cubed in it. So we have to be very careful. So we're going to be firstly using the principal value because we have a real pole involved, e to the ix, place of sine x, minus x over x cubed dx. The integral works out to pi I, residue of e to the I z minus z over z cubed at z equals to naught. How do you do the residue when z equals to naught is a repeated pole? So we have a trick. We have to differentiate this twice. So it'll be d squared dz squared of the numerator, e to the I z minus z. Then you plug in z equals to naught. So crank this out a bit. And at the end of the day, you should get minus pi over 2I. So the answer is the integral is actually the imaginary part of minus pi over 2I, which is just minus pi over 2. Finally, let's have a look at problem number 55e. Let me go to a new page to make it easier to follow. 55e. And here you have minus infinity to plus infinity cos of pi x over 4x cubed minus 8x plus 3 dx. So if you look closely, well, it's not easy to see, but poles, try to work out 4z squared minus 8z plus 3 equals a naught. You find that you can actually factorize this as 2z minus 3 into 2z minus 1 equals 0, whence z equals to 3 over 2, or z equals a half. In other words, there are two real poles. You've got two poles that lie on the x-axis, half and 3 over 2. Contour again of that type. Now you've got to contend with two real poles. So then the technique here is to realize that this integral is actually the real part of the principal value of e to the I pi x over 4x cubed minus 8x plus 3 dx. So if you work out this part here, the principal value, it will be pi I residue of e to the I pi z over 4z, sorry, that should be squared, 4z squared minus 8z plus 3 at z equals to half, plus pi I again, residue of e to the I pi z over 4z squared minus 8z plus 3, this time at z equals to 3 over 2. So both of them must be treated by the principal value idea, and then this becomes pi I, the residue will be e to the I pi z, differentiate the denominator, it's 8z minus 8, plug in z equals a half then, plus pi I, same thing, e to the I pi z over 8z minus 8, plug in z equals 3 over 2, and carry on working this out. At the end of the day, you should get a result such as root 3, so the real part will be root 3 over 16 pi minus pi over 4. Straightforward substitution from here onwards.